Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The intellectual ferment of mid-20th century physics possessed a unique character, an ambition born from the twin triumphs of general relativity and quantum mechanics. Standing at this confluence was John Archibald Wheeler, a physicist whose thinking combined profound mathematical intuition with an almost poetic zeal for uncovering the fundamental workings of nature. The program he championed, known as Geometrodynamics, represents the apotheosis of a particular classical vision, a grand attempt to fulfill Einstein's own dream of a unified field theory by taking his theory of gravity to its most extreme and logical conclusion. The ideas coalescing around the year 1954 and powerfully articulated in subsequent collaborations, proposed a universe of spectacular austerity, a world built from nothing but empty, curved spacetime. This essay undertakes a rigorous evaluation of the internal claims and conceptual architecture of the Geometrodynamics program as it was formulated in this seminal period. It will proceed by dissecting the core propositions of the theory, examining the mechanisms Wheeler proposed for constructing the physical world from pure geometry, and assessing the coherence and logical integrity of this startlingly minimalist ontology. The analysis will focus on the program's internal logic, treating it as a self-contained intellectual edifice and evaluating it on the terms its creator established. Section 1. The foundational assertion of purely geometric reality. The entire Geometrodynamics program rests upon a single, audacious claim that the stress-energy tensor, the term representing matter and energy on the right-hand side of the Einstein field equations, is a phenomenological placeholder. Wheeler proposed that the equation governing reality is the source-free equation, where the Ricci curvature tensor is everywhere equal to zero. This postulate moves the concept of matter from a fundamental substance to an emergent property of the geometric field itself. The evaluation of this claim begins with its profound reliance on the non-linear character of the field equations. In a linear theory, a sum of solutions is also a solution, and a source-free region remains unremarkable. General relativity's equations are intensely non-linear, meaning that gravitational fields themselves gravitate. This self-interaction is the engine Wheeler employs to generate complexity from a vacuum. His argument posits that the complex tessellations of spacetime curvature, the ripples and warps interacting with one another, can self-organize into structures that, from a distance, mimic the properties of matter and energy. The internal coherence of this step is mathematically sound. The non-linearity is a known feature of the theory. The evaluation, therefore, shifts from the mechanism's existence to its sufficiency. The claim's strength lies in its ontological economy, offering a universe built from a single entity, the metric field. Its primary challenge, assessed from within the framework, is demonstrating that this geometric complexity can account for the full, discrete and stable spectrum of particles observed in nature. The program at its outset presents this less as a proven theorem and more as a guiding principle, a deeply held conviction that the richness of the geometric structure of spacetime is adequate for the task of constructing a world. The argument is one of sufficiency and potential, a bet on the generative power of Einstein's equations when taken with ultimate seriousness. Section 2. The Gen is a model for mass without mass having posited a purely geometric reality. The immediate burden of proof is to construct an object that behaves like a particle. Wheeler's first and most famous creation for this purpose was the Gen, a term he coined for a gravitational electromagnetic entity. The Gen is conceived as a bundle of electromagnetic waves, or gravitational waves, held together in a confined region by the strength of its own gravitational pull. The analysis of this claim begins with the specific equations used to the coupled, source-free Einstein-Maxwell equations. Wheeler demonstrated that it is possible to find solutions where electromagnetic radiation is trapped in a toroidal or spherical region, its outward pressure balanced by the inward pull of the spacetime curvature it generates from a great distance. The spacetime around this configuration would exhibit a curvature indistinguishable from that produced by a massive object of equivalent energy, as dictated by the principle of mass-energy equivalence. The GEN thus represents a mechanism for creating mass without mass. An evaluation of this construct reveals its immense ingenuity. It provides a concrete, calculable model for how the energy of a field can manifest as localized mass. The methodology relies on finding self-consistent solutions, a notoriously difficult task. Critically, the internal evaluation must address the stability of such an object. Wheeler's own initial analysis suggested that GENs could be remarkably long-lived, their slow leakage of energy, or evaporation, occurring over cosmological timescales. However, subsequent, more rigorous stability analyses performed by others within the classical framework revealed that most simple GEN configurations are unstable. They tend to either dissipate their energy rapidly or collapse into a singularity. This finding challenges the GEN's viability as a direct analogue for stable elementary particles like protons or electrons. The claim that GENs provide a complete model for massive particles is therefore weakened. Their significance shifts to being a powerful proof of concept, demonstrating that field energy can self-confine gravitationally, a crucial first step in the broader geometrodynamic project, even if the specific implementation falls short of producing the eternal stability required for a fundamental particle. Section 3 Fabricating charge from spacetime topology. The geometrodynamic program's next great challenge was to account for electric charge. Proposing charge without charge required an even greater leap of imagination. Wheeler's proposal for this is one of the most elegant and radical ideas in theoretical physics. That electric charge is a manifestation of spacetime topology. Specifically, he modelled a single electric charge as the mouth of a wormhole. The analysis of this claim requires an understanding of Gauss' law in the context of general relativity. Gauss' law relates the electric flux through a closed two-dimensional surface to the total charge contained within the three-dimensional volume it encloses. Wheeler's argument is this: imagine a spacetime that is multiply-connected, possessing a handle or a breach connecting two distant regions. If one draws a spherical surface around one of the wormhole mouths, electric field lines can emerge from it, travel through the wormhole, and re-enter the universe at the other mouth. An observer performing a measurement of the flux through the sphere would conclude, via Gauss' law, that there is a net charge within the sphere. Yet, everywhere on the surface and within the volume itself, the source-free Maxwell equations hold. There is no charged particle substance, only a topological feature of the spacetime manifold that creates the illusion of a source. The evaluation of this claim must admire its mathematical genius. It provides a purely geometric and topological origin for a fundamental physical quantity and naturally explains charge quantization as accounting of these topological features. These lines of force, trapped in the wormholes, wrote. The internal critique, however, must focus on the physical plausibility and stability of the required wormhole structures. Within classical general relativity, such traversable wormholes, often called Einstein-Rosen bridges, are dynamically unstable and pinch off faster than light could traverse them. The model requires a stable topological structure, the physics of which is highly speculative and ventures into territory beyond the established classical theory Wheeler was using. Consequently, the claim that charge as a wormhole mouth stands as a beautiful and conceptually powerful idea, a testament to the program's aesthetic drive. Its foundation within the established dynamics of classical general relativity is, however, tenuous. It serves as an exploration of what could be possible if spacetime possessed such exotic features, a further articulation of the geometrodynamic dream. Section 4 The universe as a deterministic initial value problem, a core tenet of the geometrodynamics program, and one that reveals its deep classical roots, is its treatment of the universe's evolution. Wheeler, drawing on the mathematical work of Lichnerovich and Choquet-Bruhat, heavily emphasized the initial value formulation of general relativity. This framework asserts that if one specifies the geometry of a three-dimensional space-like hypersurface, represented by its intrinsic metric, and its rate of change in time, represented by its extrinsic curvature, the Einstein field equations then determine the entire four-dimensional spacetime geometry for all past and future times. Wheeler's argument internalizes this mathematical result into a profound physical and philosophical statement. It claims that everything there is to know about the universe, its entire history and destiny, is encoded on a single spatial slice. Physics is reduced to the study of the geometry of three-space and its evolution into the fourth dimension. An evaluation of this claim highlights the determinism inherent in the geometrodynamic worldview. The universe becomes a block, a single, static four-dimensional geometric object, and the passage of time is the exploration of its structure by an observer's world line. The methodology here is to take a well-established mathematical property of the equations and elevate it to an ontological principle. The claim's strength is its logical completeness within the classical domain. Given the initial data, the system's evolution is fixed. This provides a powerful sense of closure and totality to the geometrodynamic picture. A critique from within the program's logic must acknowledge its power while also recognizing what it implies. It presents a world devoid of chance or quantum indeterminacy. By framing the entirety of physics as the consequence of initial geometric data, Wheeler positions geometrodynamics as the ultimate classical theory, a final and complete expression of a clockwork universe, albeit one whose gears are the very fabric of spacetime. This deepens the program's intellectual chasm with the probabilistic world of quantum mechanics, a point of tension the program itself had to confront. Section 5, the deferral of the quantum realm. The most significant challenge to the geometrodynamic program was the existence of quantum mechanics. Wheeler was, of course, a central figure in quantum theory as well, and he was acutely aware of the issue. The program's internal handling of this challenge was one of strategic deferral and recontextualization. The claim was that classical geometrodynamics was a necessary prologue to a future theory of quantum geometrodynamics. Wheeler argued that before one could quantize gravity, one must first understand what, precisely, is to be quantized. His program was an attempt to identify the true, fundamental dynamical degrees of freedom of the universe. In his view, these were the components of the three-dimensional metric on a space-like hypersurface. The dynamics of spacetime was the arena in which physics unfolded for Wheeler. The dynamics of the arena was the physics. An evaluation of this framing reveals a sophisticated strategy. It presents the classical program as an essential preliminary step. The goal was to arrive at a superspace, the infinity-dimensional space of all possible three geometries, and then to define a quantum wave functional over this space. The evolution of this wave functional would then describe the quantum reality of the universe. This claim reframes the classical program's limitations as part of a larger, more ambitious research agenda. A critique of this argument acknowledges its foresight. The concepts of quantizing three geometry and the wave function of the universe became central themes in later quantum gravity research, particularly in the Wheeler-DeWitt equation, which formalizes this very idea. However, the claim that a full understanding of the classical theory must precede quantization is a debatable methodological assumption. It reflects a particular philosophical stance on the relationship between classical and quantum descriptions. The program's insistence on starting with a classical picture of geometric objects like regions and wormholes, and then hoping to find their quantum analogues, proved to be an exceptionally difficult path. The fundamental discreteness and probabilistic nature of the quantum world sit uncomfortably with the smooth, deterministic continuum of classical geometrodynamics, and the program, as formulated in the 1950s, provides no concrete mechanism for bridging this conceptual divide. In conclusion, John Archibald Wheeler's geometrodynamics program of the mid-1950s stands as a monument to the power of aesthetic and philosophical conviction in theoretical physics, the systematic evaluation of its core claims reveals a structure of breathtaking ambition and profound intellectual elegance. Its central postulate, that reality is constructed solely from the geometry of empty spacetime, is a powerful driver of inquiry, pushing Einstein's theory to its ultimate conclusions. The specific mechanisms proposed, such as the GEN to model mass and the topological wormhole to model charge, are masterpieces of theoretical ingenuity, while a rigorous internal evaluation shows that these specific constructs face significant challenges regarding stability and physical realizability. Within the classical framework, their conceptual value is immense. They demonstrated the surprising richness latent within the vacuum solutions of general relativity. The program's embrace of the initial value formulation solidified a deterministic, block universe perspective that cast the whole of physics as the unfolding of initial geometric data, its strategic deferral of quantum mechanics, framing the classical theory as a necessary precursor to a quantum theory of geometry, was both a pragmatic choice and a philosophically revealing one, which presciently laid the groundwork for future avenues of research in quantum gravity. Ultimately, geometrodynamics in its purest form failed to become the final theory its proponents envisioned. The world appears to contain fundamental quantum fields that resist a purely geometric interpretation, yet, to label the program a failure is to miss its enduring and transformative significance. Its core ideas, the importance of topology in physics, the generative power of non-linear field equations, and the fundamental role of geometry in quantum gravity, have infused theoretical physics for decades. It was a grand, beautiful, and ultimately fruitful vision, a quintessential Wheelerian synthesis of mathematical rigor and boundless imagination that profoundly shaped our understanding of spacetime, matter, and the very structure of reality.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.